Okay, welcome back, everybody. In case anybody did not pick up their test yet, there's a small number of tests still on file, so you can feel free to pick that up at the end of the class. Someone asked about the average. The average was just about 80. So there were, but it was a little bit bimodal. There were a few lower marks and there were a few really high marks, and so if you did not do it as well, it was only worth 20%, and so there's still lots of room left on the final and so forth to get the points back. The solutions are now posted. And the last assignment is posted. I realize it's a busy time for many people, probably everybody. And so if you need an extension or anything on that assignment, please just let me know. That should be okay. And our exam is right at the end of the exam period, so on the 22nd. Anything else? So we basically have this class and then one more class. I said I was going to post a lecture and I was not able to do that. I didn't have time, but I don't want to miss that last lecture where I was not able to be here. And so I'm going to post something over the weekend. And then if you can have time to look at that before Tuesday, that would be great, or you can look at them all later. Any questions about anything before we get started? Okay. So last time we spent most of the class finishing up sound waves. We talked about this colorful diagram here, which is just a schematic. We put a lot more details on it last time. But what this diagram is about is it's meant to show how the three different variables that all interact in sound waves, which are the velocity, the pressure, and the density, all interact to create the sound wave propagation. We basically found by analyzing how the pressure, density, and velocity are distributed in space, that essentially what happens is that the velocity in the sound waves it has convergence and divergence. And so what it does is it piles mass into a localized region, or it can pull it out of that region, and that causes the density to either increase or decrease. We talked about the increasing case. Then when the density increases, due to the adiabatic constraint, it takes the pressure with it. So density and pressure are tied together with the adiabatic constraint. And so the velocity moves mass around, which changes the density. The density is coupled to the pressure thermodynamically, and then the pressure gradients are what drive the changes in velocity, the accelerations. And so there's this sort of causal chain where velocity influences density, influences pressure, which influences velocity again. There's kind of like a loop. And the mechanism of wave propagation involves all three of those variables sort of playing off each other. And then that was sort of the end of sound waves. So we basically derived all the equations for sound waves. We linearized. We found the dispersion relation. We found the traveling wave solutions. And then at the end, we looked at the actual physical mechanism of the propagation. And then we started to move on. We just sort of did the beginning of this, which was discussing surface gravity waves. So these are the waves on the surface of the ocean that are probably the most familiar kind of waves that are sort of in common culture, because we can see them very easily. And I said at the beginning that the general theory of surface gravity waves has a few complexities that we're going to sort of sidestep. Because it turns out that the physics of surface waves, it depends strongly on whether the water is deep or shallow. So they're separated into these two categories called shallow water waves and deep water waves. And mathematically, what that corresponds to is it's about the ratio of the wavelength of the wave, so the distance between two successive peaks. And so, for example, in this case, this distance here would be the wavelength. And to know whether we're in the shallow water case or the deep water case, we have to compare that wavelength to the depth of the water. So here, capital H is the depth of the ocean. And the depth of the ocean varies from place to place. So if you're in the open ocean, away from like continental shelves and things like that, then an average value for the depth of the ocean is about 4,000 meters or 4 kilometers. But of course, as you get close to the beach, it's only maybe a foot deep, or maybe it goes to 0 actually right at the edge, right at the shoreline. So in the open ocean, the main source of waves is winds blowing over the surface of the ocean. So we're not actually going to talk in detail about specifically how winds generate waves. That actually turns out to be sort of a pretty technical, subtle question. But in general terms, the wind exerts a force on the surface of the ocean. It's not that crazy to think it could create waves. And so in general, when you have, say, a storm, like an extratropical cyclone, a low pressure system or whatever, that's out in the open ocean, the winds blow over the ocean, and the ocean's very deep there. The open ocean is about 4 kilometers. And so those waves, if you've ever been on a ferry or whatever, the waves are maybe a few meters in terms of their wavelength. And so those are deep water waves, because the size of the waves in terms of their wavelength is much smaller than the depth of the ocean. So we're in this second category here, that the H is much bigger than lambda, so the ratio is much less than 1. So those are deep water waves. So in general, any kind of waves that are generated by storms out in the open ocean, those are deep water waves. But eventually those waves propagate, and they come to the shoreline, and then they become shallow water, because the H, the depth of the ocean, decreases a lot to 0. Near the coast, and so that in that process, the waves transition from being deep water waves that have one kind of physics to shallow water waves that behave differently. And then there are also some other sources of waves that just tend to generate shallow water waves even in the open ocean, and these are basically tsunamis. So geological things like earthquakes can generate very, very large waves, and with hundreds of kilometers in their wavelength. So between peaks, we have hundreds of kilometers. And so in this case, we have shallow water waves, and H may be 4,000 meters, but lambda is, say, 200 kilometers. So if you have very, very large lambda, which is generally associated with seismic rather than winds, then you can also have shallow water waves, even in the open ocean. But we're going to focus on the deep water case, and the reason is that we're going to find that the deep water waves are dispersive. So this is a question, it was nice, really well done question in the midterm, is the difference between dispersive and non-dispersive waves. And so sound waves, as we talked about, are non-dispersive. All the different frequencies travel at the same speed. But for surface waves, it's not going to turn out to be that way, that different wavelengths are going to travel at different speeds. And you'll see a nice demonstration of that on the last assignment. And I'll mention, there's a little bit of a computational aspect to the last assignment, but I also included, when you go and look at it, there's a notebook file, a Python notebook that's there. That's an example that you can follow. So it should, I think, make the computation pretty straightforward. You just need to change a few things in the code. Yes?
Is assignment 5 worth marks? Because on the syllabus, we were only supposed to have 4 assignments, 5% each for a total of 20%.
Really?
Yeah. Yeah, our last assignment was supposed to be due March 16th. Let me check this. I'm on the syllabus right now, yeah. Sorry.
Oh, wow. How did I not know that?
Sorry. Yeah.
Okay. Well,
maybe if we do it, you'll take best 4 out of 5.
Yeah,
Better assignments.
For some reason in my head, I had that it was 5 assignments. But you're right, it's only 4. So I can't change that. So yeah, okay, so you have an option. So you don't have to do it, but it would be good preparation. And so if anyone does do it, I will take the best 4 out of 5. If you, and it'll be good practice either way. So you're not going to lose marks no matter what. Thank you very much for pointing that out. That's my error.
Thank you.
Yeah, I worked really hard to get that done. But either way, they're good problems. It'll be good. And there is a notebook there to help you out.
Okay.
Yeah, excellent. Thank you very much for pointing that out. That actually makes you feel less bad because it's kind of close towards the end of the semester. Okay. That's actually a little bit of a relief. Okay. Thank you. Okay. So. It's always good to have people watching. Don't want professors getting away with shenanigans. Okay. All right. So anyway, so what that assignment is about is you're going to basically show how surface gravity waves are dispersive and how different wavelengths run away at different speeds. Okay, so what we're going to do today is we're going to develop the full set of equations for describing surface gravity waves, and then I'll probably post a lecture before Tuesday that'll actually solve the equations. And then on Tuesday we can do probably mostly interpretation. Okay, but so the key setup was, so we have these two classes, and we're going to look at the deep water waves. And the setup is because we want to look at deep water. So the deep water waves are the ones that are more interesting from our perspective because they're going to be dispersive. And because we want to look at the deep water case, physically, the reason that there's a difference between deep water and shallow water is that the shallow water waves feel the effects of the bottom. So when you have a rigid bottom, the flow can't go through the bottom, like obviously, right? The water can't penetrate the bottom. And so it affects the motion of the parcels. The parcels can't orbit freely or whatever. They can't move freely. They bang into the bottom. So that influences the physics. Whereas when you have deep water, basically surface water waves, they're what's called surface intensified, which means that the fundamental reason for the waves is because the surface is free and the surface can oscillate up and down. And so what that means is that all of the sort of activity, all of the motion and all of the energy of these surface waves is mostly near the surface. So if you have a wavy surface of the ocean and then you go down hundreds of meters, you could no longer really feel that there was a wave above you. The effects die out as you go down, which makes sense because they're surface waves, right? So you wouldn't really expect to feel much all the way at the bottom. And so because of that, because the waves don't feel the bottom, we're free to set the bottom at negative infinity. So we just say there is no bottom, the ocean's infinitely deep, and to the extent that the waves are deep and they don't feel the bottom, it really shouldn't make a big difference. So that's what we're going to do. We're going to have, that's why I haven't drawn a bottom here, because the bottom is sort of all the way infinitely down. But the surface is very important. So we're going to talk about the surface in a couple of ways today. But so the idea of our setup is that the surface, if there was no waves, we say the surface is at z equals 0. That's the top of the ocean. And that's that dashed line. You can think of the z equals 0 as the average position of where the surface is. But then because we have a free surface, the actual surface at any given position at any given moment can be a little bit different from z equals 0. It could be a little bit higher or a little bit lower. And we call that difference eta. So eta is a Greek letter that looks kind of like a curvy n, like an extended n. It's spelled E-E-T-A, and that's the free surface height. And then that free surface height varies as a function of x and a function of time. So we're going to be thinking about waves in one dimension, one horizontal dimension, just x, but then also the depth is important. So this is going to be another difference between the surface waves and sound waves. In sound waves, we only consider sound waves in one dimension. So we're only thinking along a straight line with no variations in y and no variations in z, we could analyze sound waves. But surface waves are fundamentally two-dimensional because we have the direction of propagation back and forth, but then there's also this idea that they're surface intensified and they have to do with this moving surface. And so the vertical dimension is also important. And if we wanted, we could also extend it into the y dimension, but it's not necessary to do that to get the basic features. That introduces other interesting things, but you can understand lots about surface waves just by thinking about x and z. So we have here x, and we always define z as increasing upward, so all this region here is negative values of z, and z equals 0 at the top. Okay, so let's look at the equations of motion for surface gravity waves. Now I'm going to abbreviate surface gravity waves SGWs. That's very common abbreviation. All right. So our equations are basically going to be more or less the same equations that we use for sound waves. We're going to have a momentum equation and a continuity equation and things like that. But they take a little bit of a different form for this application. We're going to make slightly different assumptions. So let's look first at the mass continuity equation. Okay, so our mass continuity equation is d rho dt equals minus rho times the divergence of u. And for sound waves, it was very, very important that we were tracking the changes in density as the air was moving. And that's because in this chain, this causal chain of influence, changes in the density were driving changes in pressure were driving the velocity, and it's very, very important that the density is changing. However, in the ocean, the density is very nearly constant. So the density of seawater is about 1,025 kilograms per meter cubed, and it really only varies by, a couple of percent or something over the whole ocean. That would even be a lot. For that matter, the reason that the density varies mostly has to do with salt and temperature. So when you heat up water, it expands a little bit, that changes the density. When you put more salt in, the salt adds mass, and so that increases the density. But there's very little compressibility. So there's very little squeezing and expanding of water due to physical forces or pressure forces or whatever. Water is very nearly incompressible, as we say. So for the purposes of studying surface gravity waves, we will assume constant density. And this is a very good assumption in many situations in the ocean. For some other applications, it's important to keep track of the differences in density. For things like, you may have heard of the thermohaline circulation at some point. That involves changes in density due to heat and salt. But that's not what we're talking about here. So if the density is constant, then we can write our continuity equation implies that the material derivative of rho naught then equals minus rho naught times the divergence of u. But if rho naught's a constant, then any derivative of a constant is always 0. And so we just get rho naught times the divergence of u equals 0. But then rho naught is just a constant multiplicative factor, so we can cancel that. And so we just get the divergence of u equals 0, or writing it out in components, we get du dx plus dw dz equals 0. And so this is the simplified version of the mass continuity equation that we're going to use. And this also, when we make this approximation of constant density, and then that gives us the equation that the divergence of u equals 0, that has a special name. It's called the incompressibility condition. And it implies this idea that you can't really squeeze water to make it denser. You can to a very tiny extent, and that's actually, if you looked at sound waves in water instead of in air, this compressibility would be important. But the compressibility of water is very, very slight. So for most purposes, we can assume, or at least for many purposes, we can assume that the density of seawater is constant, which gives us this equation, incompressibility, either in the top form or the bottom form. Okay, so that's our mass continuity equation, which we've simplified to incompressibility. So now let's look at the momentum equation. So previously, we wrote for sound waves du dt equals minus 1 over rho times the pressure gradient. And so we know we're going to simplify this to some degree, because in the original formulation, this density is general. The density can vary. But we're actually going to modify this equation in another way to allow us to study surface gravity waves. And so this is basically F equals ma for fluids. And so we have the acceleration is equal to the force due to pressure forces. But can anyone suggest what's missing from this equation that we're going to have to add to study surface gravity waves?
Viscosity.
Viscosity is also missing. That's true, but that's not central to surface gravity waves. It's true that that's missing, and the full Navier-Stokes equation would have that.
Gravity.
Gravity, though, yes, gravity is the key. If we don't have gravity, we can't have gravity waves. So we have to add. So we have to add gravity to this equation to study surface gravity waves. How we do this? By adding a term to the z component equation. So our x component is unchanged. We have du dt plus u du dx plus w du dz equals minus 1 over rho naught dp dx. And so here we've made the assumption that rho is constant density. So this equation is the same equation that we had before for sound waves. The only difference is that now we've done 2 dimensions. So we're including both the u material derivative part plus the w material derivative part. But the z equation changes a little bit. We have to add a term. And so we get the material derivative as before, and we get the pressure gradient as before. And all we do to add gravity to this equation is we just write minus g on the right-hand side. And this makes sense because the left-hand side here is the acceleration. So so this makes sense because our equation, our momentum equation, is like F equals ma. So in fact we write it as du dt, and this is like A, equals minus 1 over rho grad P minus G z hat. And this is F divided by M. And so here, we don't need to worry about this too much, but here I've just written a z hat here. That's the vertical unit vector. That just indicates that so z hat equals 0, 1. And so what this means is that there's 0 effect of gravity in the x component of the equation, and then there's a minus g in the z equation. And so if this was just a regular, so if we had an analogy of a particle under the influence of gravity, we would have F equals ma, and then F is m minus mg, and so we would have minus mg equals ma, and our m's cancel, so we would just get a equals minus g. And so this is the same thing that's happening. The acceleration due to gravity is just minus g. And so in our vertical equation, the left-hand side here, this is the acceleration, or just the acceleration in the z component, I guess. This is a z, and that acceleration is influenced by the pressure gradient force, but then also there's just a term associated with gravity. Okay. So this is the key modification we need to make to the momentum equation so that our equations contain gravity waves. So we can analyze gravity waves, we need the force of gravity in there. Okay. So now we want to continue our discussion of how do we count equations. And this was one actually done on the midterm. There was a little bit of confusion about this one, the first question. And how do we know if a system is closed or not? And it's related to the idea of counting equations. So far, we have three variables. We have U, W, and P. And we have three equations. We have momentum, which gives 2. I have incompressibility, which gives 1. And so at the equation counting level, it seems like we're doing pretty well because we have the same number of equations, 2 momentum, 1 incompressibility, and we have 3 variables, U, W, and P. And the reason we don't have rho here, which we usually have, is because we just set the density to be constant. So we assume we know that. That's given. So these seem like they might be closed. But in fact, they are not. They are not yet closed because we need to specify the boundary conditions. Sorry, I heard some whispering. Is something particularly hard to read? No. Okay. All right. So in general, it's actually a little bit tricky when studying this type of equation is called partial differential equations. So they have all these partial derivatives. And in general, it is actually kind of difficult to just look at a PDE and know exactly if it's closed or not closed. It's pretty easy to tell if it's not closed, because if you have more unknowns than you have equations, you're definitely not good. Your system is not closed. But the role of boundary conditions can make the problem discerning whether it's closed a little bit more challenging. In this case, we sort of know something must be up because we have this free surface, and so the free surface has to come into this somehow, and we haven't listed this yet. So we need to incorporate the free surface, eta of x and t, to close the system. Okay. So far we've talked about our equations, we talked about mass continuity and momentum, and now we're going to talk about the boundary conditions. So boundary conditions in general are equations that specify how the variables behave at the boundaries. And I actually just want to clarify something, which is that when I'm talking about counting variables and counting equations, a few people were a little bit confused about this on midterm. When I say variables, what I mean is the dependent variables. So the things that depend on space and time. So like temperature, density, velocities, things like that. Whereas like x and time, like space and time themselves, those are the independent variables, or like the coordinates. And so when I say variables, I don't mean the coordinates. I mean u, w, and p. And what specifically the variables are, it varies from equation to equation. You might have temperature, you might have density, depending on it. But I don't mean x and time. I mean the three what are traditionally called dependent variables that are functions of the coordinates. Okay. So we need to say what happens at the boundaries. And so it turns out there are two boundary conditions for this problem that have different physical meanings. There are two important boundary conditions, kind of three, but we'll come to that. There are two important boundary conditions for this problem. So the first one is called the pressure boundary condition. This one's pretty simple. So we have the pressure field P of x and z at time. And at the surface, the pressure must equal the atmospheric pressure. So we have P of x and z equals eta of x and time has to equal P atmospheric. Okay. So the physical idea is very simple, right? That the atmosphere is pressing down on the surface of the ocean, and at the top of the ocean, the water pressure has to balance that atmospheric pressure. So whatever our pressure is, the pressure of the water, right at the top, the pressures have to match. And if not, you think about it, if there wasn't a matching, then the pressure gradient force is this derivative here of pressure. And you can imagine if you were looking down from the top, let's say here's our surface, and you had the pressure was a certain level here, and then there was a jump, and the pressure was lower inside, say, there was a gap here, delta P, then that would mean that the derivative dP dz would equal infinity. If you have a jump in a function, if there's a discontinuous jump, then that corresponds to an infinite derivative, which would lead to an infinite force. And so in general, you don't want to have jumps in the pressure unless you're taking into account other forces like surface tension that exist only at the interface. But in general, so there's pressure pushing down on the ocean from the atmosphere, and so the water pressure has to balance that right at the surface. But then there's this little bit of a mathematical complexity, which is that where is this true? Exactly where is it the case that the pressure has to equal the atmospheric pressure? But it's not at z equals 0. It's at z equals eta. Because z equals 0 is the average position of the surface, but z equals eta is the actual position at a particular point x and t. And so what we're going to do is, what we're doing at the beginning is we're writing down the boundary conditions in sort of a fully general way, where everything is going to have these etas floating around. But then because we're talking about waves, we're going to do linearization. So just like we did for sound waves, we're going to do linearization. And that's going to make the equations much, much more simple. But right now, we just want to express the physical principle that pressure at z equals eta must equal atmospheric pressure. So that's the first boundary condition. And that's called the pressure condition. And the second condition is called the kinematic surface condition. And this one is a little bit more subtle. So we actually have, here's our surface, and here's our z0. And what we're going to do is we're going to think about the parcels of water that are right at the surface. So inside this domain, there's all kinds of little parcels. On every point, there's a parcel. But then there are some parcels that live right at the surface. And I've kind of drawn this one half in and half out, but it's really it's inside the water. So there's parcels right at the surface. Right at the surface. So for parcels at the surface, we have z, the parcel position, vertical position, is equal to eta of x and t. So if they're at the surface, their vertical coordinate is equal to eta, which is the surface position. So there's an idea that the parcels, the water that makes up the surface, sort of stays at the surface. And as the surface moves, those parcels of water, they move with the surface. So we assume that the parcels which make up the surface remain on the surface. So we can then say that as the parcels are moving, they're staying on the surface. So we can take the material derivative of this equation and capture the movement. So to capture the movement, we can take the material derivative. So we get dz dt equals the eta dt. Just taking capital D by dt of both sides of this equation. And so now expanding this, if we expand, we get d by dt plus u d by dx plus w d by dz of z equals d by dt plus u d by dx plus w d by dz of eta of x and t. But there's a lot of simplifications that happen here because z is the coordinate, so it doesn't depend on x or on time. And so these are both 0. And then w d by dz of z, d by dz of z is 1. So we just get w on the left-hand side. And then on the right-hand side, eta depends on time and depends on x, because this is the fluctuation of the surface, which is moving in both time and space. But it's only defined at the surface, so it doesn't have any depth dependence. It's just a function of x and time. So this z derivative is 0. So we get on the right-hand side d eta dt plus u d eta dx. And it's important to clarify exactly where is this true. Where are we imposing the boundary conditions? And again, it's not at z equals 0. It's at z equals eta. So this condition holds at z equals eta of x and t. So we have w of x and z equals eta of x and t equals the eta dt plus u of x, eta of x, sorry. Z equals eta of x and t times d eta dx. So this boundary condition is really weird looking and complicated because you've got all these etas. There's derivatives of eta on the outside, but then also the velocities, the w velocity and the u velocity, are evaluated at z equals eta. So we have these functions, u and w, which tell us the velocity everywhere, and there's a particular value of z right at the top, which is z equals eta, and that's where we have to pluck those velocities from to specify the boundary condition. So if you were really going to use this, so we're not actually going to use this equation. We're going to simplify it first, and then we can use it. But if you wanted to use this, it's kind of a strange problem because our domain, our domain of calculation here is time dependent because we're going from z equals minus infinity at the bottom up to z equals eta, but eta depends on x and time. So how big your domain is actually depends on where you are and when you're talking about. And so that introduces all kinds of complications, and you can imagine if you're trying to solve this on a computer, kind of how do you do that? Because if you put down a fixed bunch of grid points, then where those grid points are has to be moving around to actually track how the wave works. And so for all of those reasons, the standard approach is to linearize all these equations, and then this equation is going to become much more simple to understand and also a lot easier to work with. But rather than just jump to the easy form, I think it's useful to at least give yourself the opportunity to think about what's called the full nonlinear form. The fully complicated boundary condition, the exact boundary condition, is this equation, but then we're going to work with a much simpler version. So if this seems a little bit confusing, don't worry about it really, because we're not going to work with this, but it's just something to ponder than anything else, because we're going to use the linearized version. Okay. All right. So now, we now have our full set of nonlinear equations for surface gravity waves, and they are du dt equals minus 1 over rho naught dp dx, dw dt equals minus 1 over rho naught dp dz minus g, du dx plus dw dz equals 0. These are our equations. And our boundary conditions are p of x and z equals eta of x and t equals p atmospheric, and w of x, z equals eta of x and t equals d eta dt plus u of x, z equals eta x and t d eta dx. Okay. Okay. So to actually analyze the wave physics, just like we did for sound waves, we're going to do linearization. So we will now linearize about the state of rest. And this is called hydrostatic. Hydro just means water, obviously, I guess, and static means not moving. So with sound waves, the basic state was sort of kind of easy to figure out. Basically, we had some background density, some background pressure, and then we said the velocity was 0, and on the midterm you included the background velocity being constant rather than 0. And a very nice, simple aspect of the sound wave problem was that the background state did not depend in any way on space. So the background density was constant everywhere, the background pressure was constant everywhere. But it's sort of common knowledge that pressure in general is not constant. The background pressure in the ocean increases as you go down, because you have more and more water above you, and that's why things get crushed when they go down really deep. And likewise, when you go up in the atmosphere, the pressure drops. So the state of no motion actually has a pressure that depends on space. It depends on depth. Whereas the sound waves, it did not. And so we had to be a little bit more careful in the surface wave problem to make sure that we get our background state right, and that it has this property of the pressure increasing with depth. So for sound waves, our background state was simply P equals P naught, rho equals rho naught, U equals 0, or U equals U naught. For surface gravity waves, because pressure depends on depth, the situation is slightly more complicated, but only slightly. So let's look at what our equations say. When U equals 0, so we're at rest. So we're just going to say the velocities are 0, and we have all these equations, and then we'll see what those tell us about the background state. And then we're going to consider small perturbations to that state, just like we did for sound waves, and that'll tell us about the wave functions. So, setting U equals W equals 0, and we're also going to set eta equals 0, which means a flat surface. We get. So, let's just call these equations 1, 2, 3, maybe 4, and 5. Okay, so 1, if our velocities are 0, we get 0 equals minus 1 over rho naught dp dx. And then 2, we get 0 equals minus 1 over rho naught dp dz minus g. And I'm going to put little zeros here, meaning these are the background state pressure. So when the velocities are 0, we have these two equations acting on the pressure, and our third equation, non-divergence, just gives 0 plus 0 equals 0, so that one's good. There's no worries about that one. Okay, so let's say we have a starting with the idea of a background pressure field, P equals P naught of x and z. this first equation, if you think about the background pressure field in general, it's a function of x and z. In general, that could be true. The first equation here, what does that tell us about the background pressure field? What information do we get from the first equation? Or just what does the equation say in any kind of, or does anyone have a comment on how we would interpret that equation, equation 1? What does it say about P naught?
The pressure is constant along all x values?
So right, the pressure is constant along all x values, or another way of saying it is that pressure does not depend on x. Yeah, equivalent. So, equation 1 implies the pressure P naught does not depend on x. So, P naught is equal to P naught of z. So it might still depend on depth, but it doesn't depend on x. And that makes sense, because if it's a state of rest, then you can't have any lateral pressure gradients, because that would create forces that would push the water parcels around, and then it wouldn't be a state of rest. So this here says, do you want to read this out? So it says, for surface gravity waves, because pressure depends on depth, the situation is slightly more complicated. Let's look at what our equations say when u equals 0.
Oh, thanks.
Yeah, sorry. I know it's my fault. Just feel free to yell at me. I know I'm bad. Next year, you guys aren't going to get the benefit of this, but next year, over the summer, I've convinced myself that I'm going to type the notes up. So at least, you guys got like notes for the first 3 weeks, and then not after that. But so there should be like a little book or something for the next year. Anyway, you guys don't get the benefit. Okay. So the first equation tells us the partial derivative with respect to x is 0, so it doesn't depend on x. But the second equation is different. There's this extra term here because of gravity. So 2 implies that, so we have 0 equals minus 1 over rho, and now I'm going to write this as d, regular d, p naught dz minus g. And I've changed the partial derivative to a regular derivative because we know it doesn't depend on x. So that means that there's no x derivative, so we can just write it as a regular derivative. And so we can rearrange this and write it as dp naught dz is equal to minus rho naught g. Okay. Has anyone seen this equation before?
Yes.
And what is it? Do you know what the name is? You might have seen it in 2053.
Yeah, I'm trying to remember the name of it.
It's called the hydrostatic equation or the hydrostatic relation or the
Yeah.
formula for hydrostatic pressure.
Yeah.
It's different. Hydrostatic is the big word.
Yeah.
So this is called the hydrostatic equation. And so that would have been covered probably in Physics 2053 a little bit, but these courses cover all sorts of. 2053 is kind of a course covers like a lot of random stuff. So what this says is, says that in our problem we've got two forces acting here. We've got the pressure gradient force. This is the pressure gradient force here, and then this is the gravitational force. And it says that they have to sum to 0. So the pressure force is actually balancing gravity. So if you have a column of water, so let's just imagine we have some column of water, and we look at some particular little cylindrical slice of it, then this little part of this little disk of water, there is a gravitational force acting on that little disk of water. So if there's a gravitational force on it, why doesn't it sink? Well, the obvious reason is there's got to be some other forces, the water underneath it or whatever is holding it up. And so what happens is you have this force of gravity pulling down, but then there's actually a pressure gradient force pushing up that balances that. And then that's the key element of our background state for the surface gravity waves, is that the background state is the state of rest, but the pressure is hydrostatic, that there's actually, the pressure is not uniform, and the pressure is precisely what it has to be to support the gravitational forces that are in the problem. So when you put in gravity, it gives you a pressure gradient. If we were doing this problem like on the moon or something, or somewhere with lower or light gravity, this would be a less extreme relationship. You wouldn't have as strong pressure gradient. If the gravity was zero, you wouldn't have any pressure gradient in the vertical. But this equation is very important, and the first problem on the last homework, which again is optional or for bonus points, is related to this. So we can actually solve this. So we can solve this equation to determine P naught of Z. So we integrate. So we can integrate the hydrostatic relation. And sometimes people call it relation, sometimes people call it equation. So let's integrate. I'm going to integrate from the depth Z to the depth Z equals 0, dz of dp naught dz equals the integral from the depth Z to Z equals 0, dz of minus rho naught G. Okay, so the left-hand side is an integral of a derivative. So we can just evaluate that at the endpoint. So we get P naught of Z equals 0 minus P naught of Z. And that equals minus rho naught G Z evaluated at Z equals 0 and Z equals Z. Because the integral of a constant is just Z. Okay. So the right-hand side is minus rho naught G 0 minus Z, which is just plus rho naught GZ. And our left-hand side, P naught of Z equals 0. So we just talked about the pressure boundary condition. So this is so we have now we're imagining the background state. So there's no motion, there's no waves. The flat surface is just sitting there. And so what's the value of the P naught, the background pressure at the surface Z equals 0? What should that be equal to?
PATM.
Sorry?
Like atmospheric pressure?
Yes, what did you say, Bob?
PATM.
Oh yes, there we go.
Sorry.
Yeah. So this is equal to pressure atmosphere. So we get here the atmospheric pressure, which we're just going to assume is a constant, minus P naught of Z equals rho naught GZ. And usually this is the thing we're solving for, so we want to get that on its own. So we'll do this kind of thing. So we get P naught of Z is equal to P atmospheric minus rho GZ. And this is the formula for hydrostatic pressure. I'll say note, Z is less than 0. So this is now an explicit formula for the background pressure in the absence of any kind of motion as a function of depth. And it says that at any depth Z, and recall Z equals 0 is the surface, and Z negative values of Z are inside the ocean. And so the value of the pressure at any depth Z is equal to the atmospheric pressure plus this term. And this term, even though there's a minus sign, this is going to end up being a positive contribution because we have a minus sign out front, and then Z itself is negative. So this is a pressure atmospheric plus a positive number. So as we go to deeper depths, the pressure gets larger. And the way that it gets larger is linear in Z. So if you go down 10 meters, you get a certain amount of extra pressure. If you go down 20 meters, you get double that. It's linear like that. The deeper you go down, you just get more pressure linearly. And the explanation for that is that the pressure is basically the weight of the column of water that's above your head. As you go down, you just get more and more water above your head pressing down on you. Okay. Okay. So, our background state that we linearize about is U equals 0, W equals 0, eta equals 0, and P equals P naught of Z equals P atmospheric minus rho naught G Z. And as before, in the case of sound waves, we write U equals U naught plus U prime. We're going to set U naught to 0, so that's just equal to U prime. W equals W naught plus W prime. W naught 0, so we're just going to write that as W prime. P equals P naught of Z plus P prime. And eta equals eta naught plus eta prime, but eta naught is 0, so we just get eta prime. So we have U equals U prime, W equals W prime, P equals P naught of Z plus P prime, and eta equals eta prime. And U prime depends on X, Z, and T. W prime depends on X, Z, and T. P prime depends on X, Z, and T. And eta prime only depends on X and T, because it defines the surface, so there is no vertical dependence of the surface itself. It defines the surface. So linearizing the equations of motion. So we're going to start by linearizing the equations as opposed to the boundary conditions. We had to do both. We had to linearize both the interior equations, the momentum equation, and the continuity equation. But then we have to also linearize the boundary conditions. But we're just going to start with the equations in the interior, and then we're going to do the boundary conditions. So let's start with the mass continuity. So our original equation was du dx plus dw dz equals 0. So this is really easy. So we just plug in u equals u prime. So this gives us d by dx of 0 plus u prime plus d by dz of 0 plus w prime. And these zeros are meant to represent w naught and u naught, which we're setting to 0 because our basic state is a state of rest, so there's no background velocities. And so we just get du prime dx plus dw prime dz equals 0. So that was really easy. The perturbation velocities, the linearized velocities, are compressible in the exact same sense that the original velocities were. Let's do a little rest there. So our momentum equation, we had, for our x equation, we had du dt plus u du dx plus w du dz equals minus 1 over rho naught dp dx. And so again, we get here d by dt of 0 plus u prime plus 0 plus u prime d by dx of 0 plus u prime plus 0 plus w prime d by dz of 0 plus u prime equals minus 1 over rho naught d by dx of p naught of z plus p prime. So we have all these zeros floating around, so just getting rid of the zeros, we get du prime dt plus u prime du prime dx plus w prime du prime dz equals minus 1 over rho naught dp naught dx minus 1 over rho naught dp prime dx. Okay, so let's give it a second. So when we linearize, we want to drop the quantities that we know are small, or quantities that are exactly 0. So can anyone point out, there's a few terms, in fact there are 3 terms. This equation has 1, 2, 3, 4, 5 terms. Actually 3 of them are either 0 or we're going to drop them. So can someone suggest what are some terms that are either 0 or we're going to drop here?
The ones that have 2 factors that have a prime.
2 primes, right? So this one has 2 primes, so we're going to drop that. And this one also, you agree? Has 2 primes?
Yeah.
I'll drop that. And then the last one actually is this one here, because p naught only depends on z. So p naught depends only on z. So when we take the x derivative, it's going to vanish. So it has no x derivative. So those 3 terms are 0. So we get du prime dt equals minus 1 over rho naught dp prime dx. Which is actually the exact same equation that we had for the soundings. Okay, so what about for our z momentum equation? So our z momentum equation was dw dt plus u dw dx plus w dw dz equals minus 1 over rho naught dp dz minus g. Okay, so let's plug in our decomposition. So we get d by dt of 0 plus w prime plus 0 plus u prime d by dx of 0 plus w prime plus 0 plus w prime d by dz of 0 plus w prime equals minus 1 over rho naught d by dz of p naught of z plus p prime minus g. And just getting rid of our zeros, we get dw prime dt plus u prime dw prime dx plus w prime dw prime dz equals minus 1 over rho naught dp naught dz minus 1 over rho naught dp prime dz minus g. And as before, all the terms with 2 primes we're going to drop. So we drop this one, we drop that one. And so we get w prime dt equals minus 1 over rho naught d by dz. And we actually have a formula, so we can recall that P naught of Z, we actually solved for an exact formula. It was P atmospheric minus rho naught times G times Z. So you can plug that in. P atmospheric minus rho naught times G times Z minus 1 over rho naught dP prime dZ minus G. And so here what we've done is we've plugged in the explicit formula for our hydrostatic background pressure into our momentum equation, because we're writing all of our variables as our background state plus our perturbation. And in the sound wave case, the background state was just a constant, but here it's a function. It depends on z, but we do the exact same thing. We plug that constant or that function right into the momentum equation. And so we can take this derivative. This is an explicit function. So we get dw prime dt equals minus 1 over rho naught. This derivative, d by dz of pressure atmospheric, is a constant. D by dz of minus rho naught gz, it only hits the z, which gives 1. So we get minus rho naught g. So we just get minus rho naught g here. Minus 1 over rho naught dp prime dz minus g. Within this term, we have 2 minuses, and we have rho naught on top and rho naught on bottom, and then the minuses cancel also. So this gives us plus g minus 1 over rho naught dp prime dz minus g. So the 2 g's show up, and those g's cancel. And so we end up getting dw prime dt equals minus 1 over rho naught dp prime dz, which again is the same simple form for the momentum equation, just the acceleration, the rate of change in velocity component, the acceleration, is just equal to the perturbation version of the pressure gradient force. And so we have a very symmetrical form. The x momentum equation is du dt equals dp dx times a constant, and dw dt, the vertical component, is equal to dp dz times a constant. And so this has actually completed this section. So we've now linearized the continuity equation, which was very easy, and we've linearized both momentum equations, the x and the z component, which are slightly more complicated, but it's still the same recipe. We plug in background state plus perturbations, we drop anything that's automatically 0, and we drop anything with 2 primes. And then we end up with these equations, and we know they look right because each term has exactly 1 prime. So anything with 0 primes, like for example this g term originally, that has 0 primes. So in the final linearized version, there shouldn't be anything with 0 primes, and then by our construction of the way we've done things, the g's ended up canceling out, and so we end up with an equation with 1 prime in each term, which is what we should always end up with if we're doing the linearization correctly. Okay, so that's all for today. And so next time, we're going to continue this, and by next time I mean I'm going to post a video showing this, and so if you can take a look at this over the weekend, then on Tuesday we can do sort of interpretation, and we've talked about dispersivity and things like that. But I'll post a lecture. Probably I'll try to make it not a full lecture, like maybe half an hour or something. That'll sort of conclude some of this linearization stuff, and then on Tuesday we can pick it back up with dispersion relation, dispersivity, and a few properties, and that'll wrap up the course. Okay, great. Well, have a good weekend, everybody, and I will see you on Tuesday. And if you do have any questions, even though the assignment is not mandatory, if you do have any questions, please just let me know. Okay. Thanks. Bye.
Thank you.
Thanks.